Hi guys, David here with another science update. So today the first concept that I want to talk about is something called the Silurian hypothesis, which asks, what if humanity is not the first advanced civilization on Earth? And I should say from the start that this is very speculative, and this is not necessarily like an Ancient Aliens theory channel or anything like that. We're just looking into some credible science behind asking this idea. So this article on discovermagazine.com starts by talking about a kind of interesting segment of geological history known as the Palestine-Eocene thermal maximum. And what has intrigued geologists is that in many ways this geological layer corresponds in some ways to our own experience. For instance, the carbon levels spiked, the temperatures rose, and ecosystems fell apart. And that is similar to what's going on right now, of course. We have carbon levels rising, we have temperatures rising, and we have a lot of species going into extinction. And geologists have for a long time kind of puzzled over why is it that all of this could have happened in the Palestine-Eocene thermal maximum period. And primarily they've talked in terms of different natural processes that could have triggered such severe global warming, but almost tongue-in-cheek, some geologists propose the idea, well, what if the reason that during this particular period, this 56 million year old period in time, that the carbon levels were rising, the temperatures were rising, and a bunch of species were going extinct, what if it was the same reason that it is happening now? What if there was some ancient civilized species that had figured out how to burn fossil fuels and they actually destroyed their environment? And then the question is, because I'm not putting this forward as this happened, I'm just saying, the question is, would we be able to tell from the fossil record or from the geological record whether or not that actually took place? And this gets to the idea that our current period in time, which people are calling the Anthropocene, which is related to like anthropology, like study of humans, is pretty short. So biologically modern humans are estimated to have existed for 200,000 years. And I thought it'd be interesting, I just looked up the first dinosaur I could think of was brachiosaurus. And the brachiosaurus apparently lived in a period from about 150 million years ago to 130 million years ago. So that's 20 million years. So 20 million is actually 100 times longer than the existence of humans so far. So you have species out there which have lasted at different points in time, like 100 times the length of ours, and we only really have a few skeletons of them. So the question is, if you're thinking about skeletons, if you're thinking about different chemical signatures, how much really is 200,000 years in the geological record? It's not very long. This concept becomes even more exacerbated when you consider the fact that up until probably the Industrial Revolution, humanity's impact on the long-term chemical composition of the atmosphere or of the soil was very minimal. We hadn't invented plastics, we had not done anything with nuclear energy or nuclear bombs, and we were pretty much doing kind of the same stuff as other species, but with just a little bit more flair, you could argue. They say, our seemingly indelible mark on this planet will someday be reduced to a thin layer of rock composed of the eclectic materials from which we've constructed the human world. Collectively, they make up our technosignature, the unique imprint that accompanies every technological species. So in conclusion, the original paper says that the Anthropocene layer, that's us, in ocean sediment will be abrupt and multivariate, consisting seemingly of different proxies, biomarkers, elemental composition, and mineralogy. It will likely demarcate a clear transition of faunal taxa prior to the event compared with afterwards. In other words, after this, before this, there will be fossils of many species that won't exist after us because of the impact that we've had as a species on extinction events for other species. Also, we speculate that some specific tracers that would be unique, specifically persistent synthetic molecules, plastics, and potentially very long-lived radioactive fallout in the event of nuclear catastrophe will be present. So that's some comfort, I suppose. If we end up wiping ourselves out in a nuclear war, then the geologists, the alien geologists or geologists of some future terrestrial civilization we'll have an easier time answering the question of whether or not advanced civilizations existed in Earth's past. And I appreciate this conclusion of the original paper. It says, perhaps unusually, the authors of this paper are not convinced of the correctness of their proposed hypothesis. And they say, while we strongly doubt that any previous industrial civilization existed before our own, asking the question in a formal way that articulates explicitly what evidence for such civilization might look like raises its own useful questions related both to astrobiology and to the Anthropocene studies. And also, it's just good science. You don't have to necessarily believe something to test it, and to really look at the evidence of it with an open mind is I would say is the mark of a well-developed scientific mind. So I think it's a great paper. I agree with them. I do think it's really unlikely that there were civilizations in the past. It seems like it's highly improbable for such a thing to occur, but I think the point is it's hard to know for sure just based on the geological record. The other paper that I want to talk about today is in a completely different field. It's called Cell Membrane Coated Integrity Affects the Internalization Mechanism of Biomimetic Nanoparticles. So basically the gist of this paper is it's pertaining to the field of nanomedicine. And in the field of nanomedicine, what they're doing primarily is using nanoparticles that have different medical efficacy, and then finding ways to get those nanoparticles into the right part of the body to affect a treatment. And one of the common ways that they actually do this is to take a nanoparticle and actually coat it in a cell membrane. And so as you'll recall, cells have what's called a phospholipid bilayer, which basically encapsulates everything that's inside the cell and demarcates the borders of the cell. And the body is used to looking at cell membranes, and it's very comfortable with it. So if you take some kind of nanotechnology, some nanoparticle, which generally speaking the body would not recognize and would probably not like to see, and you coat it in a cell membrane, not only does it make it easier for that nanoparticle to then traverse through the bloodstream, for instance, but it also makes it easier for it to be taken up into a cell for the actual treatment. What this article talks about is that it looks like from their characterization that this cell membrane encapsulation, which is a common feature of many nanomedicine applications, may actually be much less efficient and effective than was originally thought of. And they've developed a unique characterization method which helped get them to the bottom of this. And we're going to talk briefly about that. Looking at figure 1 of this paper will give us a sense of what the purpose and what the main thrust of the paper is. So what they're talking about is when you want to make cell membrane coated nanoparticles, you start by getting source cells for the cell membranes, and then through a process of extraction and extrusion, you usually pull away the cell membranes and then push them through a porous surface to get these vesicles and cell membrane fragments, which are then combined with a nanoparticle, which in this case, they used a silicon oxide nanoparticle, and it's this little blue sphere. And then in the presence of the silicon nanoparticles, they do extrusion or sonication to try to make fully coated cell membrane nanoparticles. But what is unclear from these techniques is the degree to which you wind up with maybe partially coated nanoparticles or even uncoated nanoparticles. So they put together a fluorescence-based assay to try to figure this out, and it's very interesting. So what they did was they took a dye, essentially a dye molecule, and they coated the nanoparticles with it, and then they added, they compared nanoparticles which were uncoated, nanoparticles which were partially coated, and nanoparticles which were fully coated, and then they added a dye quencher. And the dye quencher would only work on the segments of the nanoparticle which were uncoated. So in other words, the dye quencher turns off the fluorescent dye. So if like this sphere here, what I'm showing with my mouse, has the fluorescent coating on the nanoparticle, and then you add the dye quencher, it will turn the fluorescence off. But in the bottom scenario, where you have a nanoparticle which is coated in a cell membrane, the dye quencher can't get to the cell membrane, or can't get through the cell membrane, and it can't turn the fluorescence off. So you'll see that the fluorescent particles will stay fluorescent. And what's really interesting, and I do think it's hard to see in this picture, but in image K, what they're showing is a scan of the fluorescent particles before the addition of the dye quencher. And then when they add the dye quencher, most of the fluorescence is actually turned off, which indicates that in a typical study of this sort, most of the nanoparticles present are either only partially coated or uncoated. And I think this may go a long way to explain why some of these nanoparticle studies, the theory is there, but the medicine effectiveness is not always there. And that's maybe partially part of the explanation. The cool implication of this is that now that they have a way to actually quantify the degree to which these nanoparticles have been effectively coated in cell membranes, they're going to be able to develop much better cell membrane coating techniques. So, because in other words, if you don't know whether or not you hit the mark, then you don't know how to optimize. It's like if you were doing archery practice or something, you're shooting with a bow and arrow, and you don't actually know if you hit the target or not because you can't see. You're just like shooting, but like no one will let you look at the target. Imagine hitting a target consistently without being able to actually aim at it and find out if your last arrow hit the mark. So I think this is a pretty cool development, and it's basically just a characterization technique, but I think that if cell membrane based nanoparticle technology developers can kind of incorporate this into their tool set, I think we might see the efficacy of this type of nanomedicine increase over time.